looked at how to do the Diffie-Hellman key exchange using math, using numbers so that computers can understand it. And in this video, we're going to look at where Diffie-Hellman key exchange is actually used. Diffie-Hellman key exchange is actually used in securing the internet using HTTPS. Right? So HTTPS is based on something called TLS, and TLS is what defines the fact that two parties should do a Diffie-Hellman key exchange before encrypting data. And the main use of Diffie-Hellman key exchange is in setting up the secret key for encryption using what is called the TLS handshake. This is the part of the internet that actually uses Diffie-Hellman key exchange in production. Okay, so for a TLS handshake, there are of course two parties: the client, which in this case would be a browser, if you're using HTTPS, and a server, which would be, let's say, domain. So whenever you open any website, say domain.com, the first request that your browser makes is a request to domain.com saying client hello. It also sends a nonce. It sends a list of encryption schemes that it supports. In the previous video, we looked at an encryption scheme called the Caesar cipher. The Caesar cipher obviously is a super simple encryption scheme, but that's not what is used in practice. In practice, we use more sophisticated encryption schemes like AES and Cha-Cha. So these are the two encryption schemes that are part of the TLS 1.3 standard. Right? Okay, so the server sees this message. It sees that, okay, it's got a client hello. That means this client is trying to engage in a TLS handshake. And it checks the nonce. The nonce is just used to make sure that the client is not spamming the server with multiple requests. It's more of a prevention of DDoS. And then it looks at the supported encryption schemes and picks one. So let's say it picks AES and says, hey, I support AES as well. Let's use AES for encrypting data between us. So it would send what's called a server hello along with the encryption scheme that it picks. Right after this, the server would send what's called server certificate. Okay, what is a certificate chain? So the client needs to know that when it's opening domain.com, the data that it is getting back is actually from domain.com. How does it verify that? So before setting up this website, the sysadmin for this server setup would have downloaded what's called a certificate. And the way to do that is to go to a certificate authority and ask for a verification that says, hey, this server is mapped to domain.com, right? So the server that is identified by an IP address, something like 1.1.1.4, actually serves the website domain.com. And how does a sysadmin get this certificate? Goes to the certificate authority. The certificate authority would give a challenge to the sysadmin. If the sysadmin is actually able to complete the challenge, it would issue a certificate. So the challenge looks very simple actually. So this is a popular website for issuing certificates. So the sysadmin would go to a website like this and say, hey, I'm going to host a server on, let's say, Nginx, which is a popular server software on, let's say, Linux. And the certbot website would say, okay, I need you to do something. I need you to log into domain.com, the server, and run this command, right? And if you are able to run this command, I will assume that you actually have control over the server and that you are also controlling domain.com. So basically what the certificate authority is trying to say is the server, the physical server that is identified by an IP address and a domain name, both of them are controlled by the same person, same organization, whatever. And so the sysadmin goes to the certificate authority, completes this challenge that they are actually able to log into that said server and able to run the command that the certificate authority asks them to execute. And once that is done, the certificate authority would issue a certificate. Now this certificate is issued against what's called a public key. So if you look at this command over here, this command basically generates a public key and a private key. And as part of executing the command, it sends the public key to the certificate authority, and the certificate authority issues a certificate for this public key. And the server would store this private key securely on the server. This private key is not to be shared with anybody. Anybody who owns this private key owns the identity of being the owner of domain.com. And the server is sending the certificate as part of the TLS response, the TLS handshake response to the client. Okay. So now the client has this certificate. It will check for two things. One, is it domain.com? is the certificate chain actually that of domain.com, and 2, is the certificate authority that issued this certificate a trusted authority. So all the trusted authorities called root certificate authorities are stored on a browser by default, right? So if you go to settings on Firefox, it might be slightly different on Chrome. You should be able to see, there you go. So you can see all the certificates that have been installed over here, and this website that we saw over here issues a certificate that would show up over here under the name of IdenTrust. Should be here. Yeah, there you go. So your browser already supports by default any certificate that has been issued by this website, because this is known to be a trusted website, and there are dozens of trusted websites that Firefox supports or Chrome supports, and all of them are inbuilt into your browser. So as long as the certificate shared over here belongs to domain.com and is issued by one of the trusted certificate authorities, the client would say, okay, I accept this certificate. Okay, till this point, what both the client and server are trying to do is figure out whether they want to even engage in a Diffie-Hellman key exchange. They want to weed out all the spam. The Diffie-Hellman key exchange, however lightweight, it is still like a little bit of computation. They don't want to do that computation without being sure that they are actually speaking to the right persons. So up until this point, we've just been trying to figure out, hey, should we indulge in a Diffie-Hellman key exchange? If the client sees that, okay, the certificate is not from domain.com, or the certificate that has been shared is not a certificate that I trust, the client would just simply close the connection. Right? Just close the connection and move on with life. The server will then see that, okay, the connection is still open, and it will send what's called the server key exchange. Okay, so now the Diffie-Hellman key exchange has started. So the Diffie-Hellman key exchange involves a generator. So the server picks a random generator, sends that across. Okay, then the server would have to select a private key, not this private key, a different private key. Let's call it B. And it would generate a public key using the generator, which is G to the power B mod P. So this is the public key, right? And then it sends G power B mod P, and it also sends P. And additionally, over here, it sends what's called a signature. Now this signature is important. The signature basically is a signature on top of all of this data saying that, hey, the person who is sending this data is the same person or the same entity that has the private key to the certificate that was shared in the previous step, right? Okay, now what happens if this signature is not present over here? There could be a malicious entity that could send its own G dash power B dash and P dash B dash. And let's assume this data packet came to your browser before this did. There's no way for your browser to say, hey, which of these two should I believe? Okay, fine, I verified the certificate in the previous step, but what if in this step, the malicious entity has been able to tap into the wire and feed this data into the wire that is actually going into my computer? So how do I distinguish between these two? The way to distinguish between these two is using the signature. Now, this signature is going to be produced by the server that has access to this private key. And the malicious user, of course, does not have access to this private key. So will not be able to generate the signature that is corresponding to the certificate that was issued by the certificate authority and that was shared in the previous step. So all of these conditions together cannot be satisfied by a malicious entity. So that's how you know that the key exchange that you're doing, the Diffie-Hellman key exchange that you're doing over here, is actually with the entity that you want to engage with, that is domain.com. Okay, once the client receives this key exchange message, it picks its own private key A and sends a client key exchange in which it would send G power A mod, right? Basically, it picks a private key, generates a public key, which is G power A mod P. This G and P are exactly the same as what was sent by the server, and sends that across to the server. Okay, so the key exchange has been done. The shared secret can be set up by the server, G power AB mod P, and the same by the client, G power AB mod P. Yeah, both the client and the server have established a shared secret, and then they would just say, done, and then start encrypting data and send it across. So this is where you can put in your private information, let's say like your credit card, your SSN or whatever, encrypt it and send it across to the server, and be 100% sure that there is no malicious entity that can listen to this data, can tap into this data, and be able to actually read your credit card information. And finally, I also want to recommend this interactive website, xargs.org. It's really good. You can actually go and look at what exact messages are being sent as part of the TLS handshake, like literally byte by byte explanation, right? So you could just open up any of these requests. As we saw, you can see the certificate being sent over here as part of the key exchange. We saw the public key, the signature. So basically everything that we talked about over here, you can get a much more fine-grained understanding on this website. I really recommend it. Cool. So yeah, we've looked at the TLS handshake as to how Diffie-Hellman key exchange works in production for HTTPS, especially the context of securing the internet. And in the next video, we're going to be looking at some of the shortcomings of the TLS handshake. There are good reasons why those shortcomings exist, but we'll look at what those shortcomings are, why they exist, and how we may overcome them. Cool. See you in the next video.